So essentially what happens with an aromatic compound, you have a single bond here and a double bond there. That's what you would presume. But if you were to measure the length of a single bond is always longer than a double bond. So what they found, and that's what they expected it to be, so when they used a mass spectrometer and different UV spectroscopy and IR, this is what they would have expected to occur, that you would have. Now, what actually was the case, which was a big change, if you like, what actually was the case, redraw that. See. So instead of it being the structure where you have single and double bonds, like so, between them, what actually is the case is that the carbon-carbon bonds are all the same length. So instead of having individual double bonds, individual single bonds, you still have the sigma bonds, all the single bonds, but the double bonds, the pi bonds, remember that's the second bond that is present when you have a double bond. The pi bond is the side-on overlapping of the p orbitals here. Instead of the electrons just being located in that one area there and there, the double bond, the electrons are actually spread out among all 6. So we indicate that with a circle, you see. So rather than us having, because what actually turned out in the spectroscopy is the length of those carbon-carbon bonds, they were actually all the same length. So the carbon-carbon, so they were and the funny thing is they were neither double nor single bond lengths. So they were actually an intermediate between the two. And now a lot of the time this is not drawn, but the hydrogens are not marked in, as I said earlier, but we'll mark them in here today. You would also still have that hydrogen off every one of the carbons as you did earlier. So it's a really unusual thing. So instead of the bonds being localized as you would have expected, you know, a double bond localized here, here and here, they're delocalized. So it's like localized flooding is in one area, whereas delocalized flooding would be spread out. And that's what occurs here. The bonding, if you like, is spread out among all, the pi electrons only are spread out among all 6. So you get this really unusual phenomenon that is known as delocalized bonds. And that's what benzene is. Now a lot of the time benzene is just drawn like so. You know, remember each corner you may assume that there's a carbon there, and when you have that circle in there, the delocalized electrons, you may also assume that there's a hydrogen off every carbon, giving it still, you know, it's neither, if we were to draw it again, C, and C, there's not a good diagram, 1, 2, 3, so it's neither double nor single. Instead, it is, you have 6 carbons around in a ring, as before, connected with single sigma bonds. The difference being is the electrons are delocalized, or spread out. The pi electrons now are spread out around the benzene ring. And benzene ring bonds are said to be delocalized for that reason. They are neither carbon-carbon single bonds, which you would see here if you like. They're neither this nor this. They're an intermediate between the two. And the bond lengths indicate that, as would be shown. That's why we represent it in this ring, rather than having just double bonds here and single bonds here, or kind of a mixture. So that's how it's normally drawn. The bonds in the benzene ring, you see it's neither this nor this. It's an intermediate between the two. And that's a nice way of thinking of it. So we draw it in this way for Leavensert. Now sometimes for bonding, anyway, let us not get into that. But yeah, and there's benzene once again. And then there's the delocalized pi electrons. So you see the sigma electrons are still the single bonds, if you like. It's the pi electrons, the second pair of electrons in every double bond. They're the ones that are different. There's methylbenzene or toluene, and there's ethylbenzene, ethyl. And remember we went through those, the alkyl groups. Methyl is methane without one hydrogen, because instead of that hydrogen you have this benzene ring. And there's ethyl, you see it's minus, that carbon's missing a hydrogen, because again it has a big benzene ring. I drew that in paint, so that's why there's a bit of a kink in that, but there shouldn't really be. And that's ethylbenzene and methylbenzene. And there's some other ones, there's propylbenzene, there's the propyl group, and there's the benzene ring. Like, that's the extent we're going to Leavensert. Not a huge amount, but you should know that they're delocalized pi electrons. It's unusual because they are neither double nor single bonds. They're actually a spread out of the double bonds. So they're called delocalized electrons. Because remember, obviously, electrons are made out of, or bonds are made out of electrons. TNT is an explosive. That's known as trinitrotoluene. So you can imagine where that name comes from. You have the nitro part of it. Naphthalene as well. You see that in a lot of substances. That's on TV sometimes as well. It's two benzene rings effectively stuck together. There's a carbon there and a carbon there. And as you can imagine, there's 1, 2, 3 bonds there, and then you have one off to a hydrogen. Actually, you don't have one off. There'll be a double bond there. The physical properties of aromatic compounds being non-polar, they don't dissolve in water. They're non-polar, you see, because it's made out of hydrogens and carbons. There's not a big electronegativity difference between those, so they effectively give rise to a very similar electronegativity, and they're neither double nor triple. So we've gone through a fair bit of that. We will look at organic chemistry or aromatic chemistry again, but just to give you that idea that the benzene ring is neither a double bond nor a triple bond. It is delocalized electrons. It's an unusual phenomenon, and very unusual for Leavensert chemistry. Now, to be quite honest, benzene rings are part of an awful lot of compounds that we deal with in everyday life, but it's just to be clear that we have mentioned it here as well. And that kind of brings us to the end of aromatic and aliphatic hydrocarbons. We could have a look at this, like, would you be able to name that compound? And I'll give you some of these in the test. If you count the longest number of carbons, 1, 2, 3, 4, 5, 6, 7. Try, is there any other? 1, 2, 3, 4, 5. No. 1, 2, 3, 4, 5, 6. No. So 7 is the longest. So that'll give you heptane. And then you say that this group is off it and this group. And you need to keep the numbers as low as possible. So I would call this, if I start at this end, 1, 2, 3, 4. That'll be 4 would be the first methyl group of it. If I start at this end, 1, 2, 3. 3 would be the first methyl. So I'll start from this end. 1, 2, 3, 4, 5, 6, and 7. So that's the carbons numbered. So we know that it is in fact heptane, because that's the most number of carbons. 1, 2, 3, 4, 5, 6, 7. ANE. Then you have 2 methyl groups of it, so it's di for 2, methyl, and that goes before it. Remember, this is just a bit of revision. And then you will put the 3, 4, and that's just a nice example of some revision of naming compounds.